everyone, today we are going to see about closed graph theorem. So B and B dash are the Banach spaces. T is the linear transformation of B into B dash. For open mapping closed graph, the difference lies in up to this is there exists a continuous linear transformation. Here just a linear transformation. So it is a linear transformation of B into B dash. Then T is continuous. The T is continuous means if and only the graph is closed. For that we have taken that T is continuous. Continuous definition implies xn tends to x naught, t of xn tends to t of x naught. So the graph of t is t of g can be represented comma t of x, that x belongs to d. Okay, subspace. Okay, is closed the graph, it will be closed graph. So we have to prove that it is closed. For closed we have to prove that for closed we prove a bar equal to a. So t of g bar equal to t of g. First we take some point x naught comma y naught belongs to t of g. So we have to prove that it is a closed t of closed, there exists definitely x naught y naught belongs to t of g bar means it is a limit point. Definitely there exists a sequence that will be converges to x naught y naught. So there exists a sequence x naught comma t xn comma t of xn in t of g itself. So there exists a sequence xn comma t of xn in t of g. Then there exists xn converges to xn comma t of xn converges to x comma x naught comma y naught. That xn converges to x naught, t of xn converges to y naught. So y naught can be written as t of x naught. Okay, transformation of x naught is equal to y naught. So t of xn converges to t of x naught. This t of x naught, if x naught belongs to b means we get x naught belongs to b means we get as the given x naught comma y naught belongs to t g bar. Y naught instead we get t of x naught. So x naught comma t of x naught belongs to here what we have, we take tg bar, but this is under the closed graph of form. X naught comma t of x naught will belongs to t of g. So we take tg bar, but we get this term as tg. X naught comma y naught we take, but x naught comma t of x naught that will be under the transformation tg. So x naught comma t of x naught belongs to g, tg. We take x naught comma y naught belongs to tg bar, but we get x naught comma y naught belongs to tg. So tg bar contained in t of g. But already we know that a bar is contained in a is contained in a bar. So tg is contained in tg bar. From 1 and 2 we proved that tg equal to tg bar. Then what we do means prove that is necessary condition, this is the sufficient condition. Given tg is closed and we have to prove that t is continuous, we have to define the, and for proving continuous we have to define another norm and have to say that have the same topology. So let us define the norm of the space b to be denoted by b dash as x belongs to b, and norm x1 is written as norm x plus norm t of x. Here norm 1 satisfies the conditions of the norm of the linear space b equipped with the new norm is denoted by, and the new norm is denoted by b1, and the new norm denoted here is b1. So thus b1 is the norm linear space. Also norm linear space, norm t of x is less than or equal to norm x plus t of x, because t of x if we compare means if some positive norm is growing, positive norm lies means we get norm t of x less than or equal to norm x plus norm t of x. So it will be definitely what x norm x plus norm t of x is norm x1. So hence we consider t as a mapping from b1 to b dash is bounded. We consider the mapping b1 to b dash is bounded, which means continuous. We have to prove that for proving a continuous we have to prove that b and b dash have the same topology, and if it is homeomorphism is we imply it is same topology, and we if it is homeomorphism means we imply t is continuous from b on to b dash. Okay, b on to b dash. So to prove that we need to know need to show that b1 is complete. Okay, b1 is complete. Let x1 be the xn be the Cauchy sequence in that new norm. We have to say that B is a linear space. Okay, definitely it is a non-linear space. So non-linear space means but B is the Banach space, means it should satisfy the complete condition. But here is just a non-linear space. So to for that Banach space, we need to show that B1 is complete. So Xn be the Cauchy sequence in B1. So norm Xn tends to norm Xn minus norm Xm tends to 0 as n comma n tends to infinity. So and the new norm can be defined as otherwise norm of Xn minus, because mm, x is x1 can be written as norm x plus norm x t of x. So xn minus xm plus t of xn minus t of xm tends to 0 as m comma n tends to infinity. This term norm plus norm of t of x minus t of xm tends to 0 as m comma n tends to infinity. This norm xn minus xm tends to 0. This t of xn minus t of xm also tends to 0. So xn is the Cauchy sequence in m, but t of xn is the Cauchy sequence in m dash, because we consider this generally we consider this as B and this as B dash form. So xn is the Cauchy sequence in B and t of xn is the Cauchy sequence in B dash, but both B and B dash are also Banach spaces because it is a complete. So it will converge. Xn tends to xn B and t of xn converges to y in B. So now we show that xn comma t of xn. Xn comma t of xn is the Cauchy sequence in the graph of t. So xn comma y t of xn is the Cauchy sequence in the graph of t, which is given to be closed. So which is given to be here is t of g is closed. So xn comma t of xn is the Cauchy sequence in the, we have to prove that it's continuous. So it is a Cauchy sequence in the graph of t which is closed. So xn comma t of xn is converges to x comma y. So converges to x comma y, that is x comma y belongs to t of g. So x comma y belongs to tg and y equal to t of x. So new norm xn minus x, that is norm of xn minus x 1 equal to norm of xn minus x plus norm of t of x minus x. So t of xn minus t of x is y. So xn minus x plus t of xn minus y. So xn tends to x in b1 b1 bar means definitely it will also goes to 0 as n tends to infinity. So b1 is complete. So b1 is a Banach space. We shall prove that there is a homeomorphism between b1 and b dash. So for that we need to prove that identity map from b1 to b dash I of x equal to x. So identity map has 1 to 1. So norm I of x equal to norm x less than or equal to norm x plus norm t of x less than or equal to norm x. So it is less than or equal, I of x is less than or equal to norm x. So it is a bounded and so if it is bounded means it is continuous. So it is 1 to 1 or 2. By the definition it is homomorphism from one Banach space to another Banach space. So now T is a continuous from B1 to B dash, hence it is a continuous homomorphic. Hence by the Banach theorem itself we know that what is the Banach theorem means. B and B dash are the Banach spaces. T B 1 to 1 continuous linear transformation of B onto B. Then T is a homomorphism. In particular, T inverse is automatically convergent, continuous. So we have all the forms 1 to 1 onto and 1 to 1 onto. Then it will have a homomorphic image. So T inverse is continuous. We have proven that B dash to B, so T inverse is B to B dash is continuous. Hope you all understand and thank you.